it's always complicated to decide what title to put on as selecting and enabling effective cost savings through innovative heat transfer enhancement technology. Actually, I started this, well, next year will be 40 years from when the moment I decided that I needed to do something, prompted by my father-in-law, who was a prof of chemical engineering at the University of Birmingham. And he thought I needed a project. So I did. And the answer was, we needed to find a better answer to how to get more heat out of a tube. I can't believe that it's taken 40 years and spending all that time figuring it all out, but it is. And at this stage, I won't go through the history because there's some technology to show you, but I'm actually standing here with a company where we have representatives worldwide. We have about 40 projects a month coming through. We sold to 40 countries last year in our business, so I think most companies and countries have had some degree of our technology. My aim is to bring more of this to India. I hate to say that India isn't at the forefront of this. It's at the forefront of many things, but I believe there's a lot more we can do here, and particularly in the saving of energy. I've been listening to conference speakers today, and I really do believe that you're committed to improving plant performance. So let's make a start at it. One of the things, it's not the only thing we do, but one of the principal things we did many years ago was to find a solution to enhancing heat transfer. The idea, of course, of modifying the flow patterns inside tubes in order to get more performance from them. This is a very simple device in a sense. It's made of wire, it can be made of any material. It touches the tube wall, it's wound in a particular way, it's very strong, and it simply fits inside the tube. It's not a mechanical part, so it can be pulled in or taken out or whatever. And the density of it can be changed. If you were looking at it as mass transfer, you'd say it was a packing. But this is a packing for a tube. So when we think about heat transfer in a tube, we think about laminar flow, transition, turbulent flow, and so on. And so the more difficult fluids, those that have a high Prandtl number, where viscosity and conductivity are the controlling ones, and then you would actually build up quite substantial boundary layers. If we could take away that boundary layer, how much heat transfer could we get if it wasn't there? The answer, of course, is a lot. How much? Answer to that one is anywhere between 2 and 20 times the rate of heat transfer. That's a lot. So according to how we make these things is according to how much heat transfer you get. But you have to make some modifications, and we'll explain that as we go. Fixing. You can fix them in a tube. You have little plates that fit on the end. They can be taken off. We can even get at those inside plug-head air coolers. Air coolers being important in the future, particularly because of the reduction of water. So these are very important in the optimization. At the other end, there's a loop, and you can put a wire through the loop. Therefore, it's held in place. If you want to take them out, you clip the wire off, you pull them out, and you can put them back in again. So this is a product that can be removed, put back in. Rarely is it. Even in dirty services, the amount of replacement ones for existing projects is very little. They are lasting a very, very long time, which is very interesting for us, particularly on refining services. This is I'll just stop it for a moment. There's a glass tube, just a QVF tube. It's got some dye in it. That dye will stay at the wall because it's laminar flow. There are no dynamics inside to take it off the wall. And that's going to be there way up beyond 25,000 Reynolds number. It doesn't disappear at 2,300, right? It's way up there. All you're doing is mixing in the center when you're at transition. You're only mixing towards the center. Okay, let's go. Whoa. Let's just run that again. Here we go. So this is at 500 Reynolds number, and you'll see it transfer across, and you'll see it'll come up off the wall. Even at 500, we can take the fluid off the wall. That's a very low Reynolds number normally. Here, we're at 2,000 Reynolds number, and within one diameter, in fact, within the tube sheet, it will have mixed the fluid up before it gets to the end of the tube where it does the heat transfer. And what you're looking at there is something like 5 to 6 times the rate of heat transfer. And yet the object itself is about 95% free area. So even if you have solids, it'll flow through it. That's the one that worries of people. So don't be so scared about it. It's very, very effective indeed. So what does it do? Where's the benefit for it? Well, here's two simple things. Keep it simple. Let's show something first of all. A simple air cooler, 2 fans. Now, the one on the top, the drawing on the top, is proportionally correct with the one on the bottom. That's to say, both of them do the same duty at the same pressure drop. Now, the big one is 8.5 ton. The little one is 2.2 ton. I forgot it for a moment. It's 2.2 ton. Wow. But the pressure drop is the same. And when I go through the detail of it, you'll understand. So the big one has 46 tubes in a row. It has 6 rows of tubes. It's 8 meters long, and it's 8 passes. You need 8 passes because you can't get enough heat transfer in 8 meters because you only get proportionally small amount of heat transfer per unit pressure, per unit length. Whereas the small one is only 30 tubes. It's only 3 rows, it's only 3 meters long, and it's 1 pass. So you're doing the work of 48 meters of plain tube, and you'll do that in 3 meters. And you'll do it at the same pressure drop. Remember, heat transfer is proportional to Reynolds number. So as you increase velocity, you only go up about 20% per unit of pressure drop. Whereas, if you then look at the pressure drop itself, that goes up as a square law. So you're chasing your tail. If you want to keep pumping faster and faster to get more heat transfer, you're not going to win because you can't get it fast enough to shear at the wall to get the mixing to get the heat transfer. You're better off to go 1 pass or 2 pass. All right? So there we are. And the punchline says, okay, what about the energy? Well, the big one is 11.8 kilowatt, and the little one's 5. And you're paying for that 24 hours a day. So if you want to find something that's truly energy saving, this is it. And there aren't that many things you can do with refineries to recover energy. But this is one of them, definitely, is a winner. Oh, I'll back up. This is a similar sort of thing with the shell and tube, of course. I just showed an air cooler as one part. Both of these do the same duty on the same basis we've been talking about before. The little one at the bottom there, I can read it from here. You're looking at 1,500 tubes in the large one. You're looking at 680 in the 689, the small one. I think we've got a coefficient somewhere. Tube size coefficient goes from 51 to 295. Very substantially different. And of course, from a cost point of view, very much less. And from a weight point of view, and from a shell thickness. It's quite often we have projects where you'd have 20 shells, and we take that down to 10 on a new project. Things like desalting units and things like that, where you're looking to process. There's a couple of studies just to show. I can only show a little bit. We've only got 50 minutes of this, but show you a little bit of the sort of projects we have. And as I said, it's about 40 projects a month coming through. This is a graphite vent condenser. And of course, you're looking to say, we're trying to reduce the amount of gas going up the stack and wasting it. If we can condense it, we can probably sell it. So what can we do to it? Well, first of all, you've got to understand it. So you better do your homework. So we will run full-time employee on CFD, PIV, and so on, in order to understand the flow patterns inside tubes. Here you're looking at the vapor weight fraction as it comes down. You're looking at the position of condensing at the point where you're going from a vapor into a liquid. Whoa, there we go. After the revamp, you're able to actually pull it down. The weight vapor fraction is substantially better. You've gone from 100% to, where are we, 0.99, and then we're at 0.975. So I'm saying that the homework you have to do in the engineering, good chemical engineering homework, thoroughly studied before, and then you can make a guarantee if you understand what's going on. When you look at the result of this, you're looking at pulling it down by another 5 degrees C, lower outlet temperature. There's a minor increase in pressure drop, increased concentrate mass flow, more than 10,000 kilograms per year of the product. And you, of course, you're avoiding, in a sense, putting in a new exchanger, if you could afford to do that within the system anyway. That gives you a saving about $258,000 a year, even for that amount, as a value. That's just a little one. It's a little graphite exchanger can save you. It doesn't cost much to do the studies. It doesn't cost much to retrofit. This isn't major capital expenditure. Paybacks are, what, 3 months to 18 months, maybe 2 years, something of the sort. It's the sort of thing that I think all plants should at least take a look at and see what might be possible. Here's another one, paraxylene, feed effluent exchanger. It's actually in Gough in Germany. It used to be BP, it's another company now. This is 12 meters tall. It's 40% quality product going in. They're looking for heat recovery, and you find most plants, this is a refinery of course, you find most plants are running at pretty well full capacity as far as the furnace is concerned. You can't do much with a furnace. They're a very large integral part of a process plant. You can't rush out and buy another one of those to improve your plant. You may be able to do a bit to burners and so on, but you can do an awful lot about recovering the heat you've already paid for. So that's what we're looking at here. Okay, so it's shell side, it's paraxylene effluent. On the tube, it's feed. The flows you can see, I don't think we need to talk too much about those. Temperature now at 403, 138. On the tube side, 94, 327. This is as existing. Heat transfer coefficient, of course, is more in this case on the shell side, and about half, a little more than half on the tube side. So the controlling coefficient is on the tube side. That tells us we can do something there to pick up that coefficient to try and meet. I mean, in an ideal circumstance, the heat exchange is correct when it has the same coefficient both sides. So here we're looking at saying we'll improve that. Duty at the moment is 19.7 megawatt. 1,734 tubes. When we were looking at the, I got that right. We're looking at the analysis of this as you go along it. Then your heat transfer, your shell side heat transfer coefficient will drop when it gets to a point of vaporization. So you can see that spike and then come down. The tube side coefficient will in fact go up and then level out again. But you see a spike there in the middle where the green changes direction, the blue one there changes direction, which is the tube side one. And here, at that point where you vaporized, the problem has been how to get more out of it. And the pressure drops are different within the two-phase flow section than it is in the sensible heat of the fully vaporized material. That means we could change the density of the Hytran product that we put inside the tube at that point. So we can change the density and enhancement as you go along the tube, if you know where to do it. In this case, we did it at 7 meters. Of the 12 meters, 7 meters at one density, connected to another 5 meters at another density. And that gave us the perfect result we wanted to achieve. And this is where it is. You'll see just on the top there, a lower density one in this first part because of the higher pressure drop, and a little bit more dense in the outer one. And you can see the curve as it goes down there from the pressure drop point of view. Okay, what are the benefits? Well, you could say there's no requirement for a larger fired heater. Well, that probably wouldn't be an option anyway. in a sense, but you're running at full capacity. You want to take what recovery you can. Mostly people don't recover energy just for the value of the energy. Energy is too cheap for that. They'll recycle it into increasing the performance of the plant and put in greater throughput, generally speaking, I'm saying. So no change to the pipework, no additional civils. Your heat transfer in the superheated region increases by 48%. The reduction in the duty, or you could say the added duty, is 0.8 megawatt. So that's quite an amount of energy that you've recovered. Essentially, you could say you've saved 1,700 tons per year of CO2. That's in the value. You've achieved 17.5% increased throughput on the plant. That's got to be a huge value. So the empty tube equivalent, if you wanted to go and buy a new Texas tower, it would cost you over $1 million. That's without installing it, even if you had the space for it. So this is a very, very, very cost-effective solution to increasing. The most important, of course, is you must do your homework on all the studies. We have to give a warranty on the performance of that we provide. We stand by the calculation we make. We share them equally with the clients we're working with, backwards and forwards, until we're all satisfied that this is what it's going to do. We had one a little time ago in Russia, and that's very complicated. 30,000 tubes, 6 giant heat exchangers themselves, condensing, maldistributing of flow. Very difficult indeed. Took 18 months of calculations backwards and forwards, but eventually they agreed that's what they needed to do. In truth, there was not much else they could do on the plant. There was no other way of recovering heat. You've got to do something. You can't change it all. And when we finished, very conservatively, we pulled out 2.2 megawatts. And that was conservative. Now we've got the data, we can go back again. Oh, we'll give it another megawatt because we can replace them again. So you can step down this without taking risk. If you know what you're doing, you can do it without risk. Okay. The concern people have is, and I remember this because I remember starting the company, and everybody would say, well, why don't you come back when everybody else has used it? It's very disheartening when you start a company and your heart is in it and nobody wants to. Everybody thinks it's great, but nobody wants to buy it. Well, there you go. 38 years later, here they are. There's some references. I don't know whether you can read any of the names there. It's quite small for me. Chevron, Petronas, Valero, PTT, Thailand, Samsung, whatever. Now, there's 9,200 of these, and I don't want to waste all your afternoon looking at them all, but we have a wonderful database. So we can actually go through that and find the references we need to support the projects we provide. Okay, this is getting boring. The important ones are the Indian ones, because they're local. And we have a few. And let me say, for those people who see their names up to their companies, thank you very much for the order. I hope you're enjoying our products in it. For those that haven't so far, maybe we can actually work with you in the future and help you improve your processes. And the only other thing I wanted to say was thank you very much.